Hey hackers, Blue Cosmo from CCS here, and welcome to Module 2 for the Introduction to Cryptography course. This module is Symmetric Encryption, so let's just dive right into it, right? So you can see I have this image here in front of me. Now I did draw this image myself, and it is on the course overview if you guys want to have this image saved or whatever. Now this is Symmetric Key Encryption. Now, again, you guys should know the vocab by now. So you should know what an encryption is, you should know what a key is, what plain text is, ciphertext, all this, right? Now you may not fully understand what the key is because we haven't completely dived into it, but you should still know the vocab and all this other stuff, okay? So, this is how symmetric key encryption works. We have plain text right here. Now if we want to encrypt it, we have to use some sort of key, all right? Now I'm going to dive into how we can use keys and stuff to encrypt and stuff. That's why you download this GitHub repository, right? I'm going to show you guys how to do this, right? But for now, just go with me, all right? We have plain text. It can say Apple, or it should be some sort of email, message, whatever. It's human readable. It's plain text. Now we encrypt it using some sort of encryption key. Now this encryption key will be used to create this plain text into ciphertext. So now we can't read it. It's a bunch of random symbols and characters, right? All right. And now we went from plain text using this key to ciphertext. All right. Now, if we want to decrypt it, we would have to take our ciphertext, use the same key, and use the same key that we used to encrypt to decrypt. All right. Now it's called symmetric because look, if I split it in half, you can kind of see it's the same thing on both sides, right? It's called symmetric because it's using the same key. It uses the key used to encrypt and the key used to decrypt are the same exact key, right? That's why it's symmetric. It's not because you can like split in half. I was just pointing that out, but you can kind of see how we can go from plain text to ciphertext and then back to plain text, and we'll all do that using the same key. All right. Now, if you want this image, again, it's on the GitHub repository for this course, or the course overview, if you will. So there you go. Now, let's kind of go into some definitions, right? So symmetric encryption. This is a ciphering algorithm that uses the same key to encrypt and decrypt text. That's what symmetric encryption is, right? Now, symmetric encryption is faster than asymmetric encryption, and asymmetric encryption is going to be the next module that we're going to dive into, all right? So next up, we're going to talk about the Caesar cipher. So Caesar cipher. All right. Now the Caesar cipher is an encryption process. It was named after Julius Caesar because it's believed that he used it as a way to encrypt messages amongst his soldiers during times of war or with his army and things like that. Okay. Now it works by moving or shifting letters down the alphabet by a certain number or index. All right. Now, I do have a live stream where I programmed the Caesar cipher by using Java, and again, it's linked in the course overview if you want to check it out. If we go to the course overview, you can see here. All right. So let's take a look at this. I'm going to zoom in a little bit so you guys can see a little bit better. So here we have our plain text indexing. Now this is an example using a shift of 1, okay? Remember, it works through shifting letters down the alphabet. So we're shifting one letter down the alphabet, all right? So with the normal plain text indexing, the one that you may be familiar with, the one that, you know, English alphabet indexing uses, we have this plain text indexing, right? So the letter A has an index of 1. The letter B has an index of 2. The letter C has an index of 3, and so on, right? Z would have an index of 26. Now, when we use a shift of 1, or shifting 1 letter down the alphabet, if we're basically shifting from A to B, B to C, C to D. So now B has an index of 1, and C would have an index of 2, and D would have an index of 3, all the way down to the letter A, which would now be 26, and Z would be 25, and etc. All right? Which means if we have the plaintext hello, and we encrypt it using the Caesar cipher with a shift of 1, it would be IFMMP, because H, 1 letter down, would be I, E, 1 letter down would be F, L, 1 letter down would be M, and O, 1 letter down would be P, right? Because O comes before P, H becomes before I, E becomes before F, etc. Now, note each character, shift over by 1. That shift is our key. So this shift of 1, our key is 1. If we had the shift of 2, our key would be 2. If we had a shift of 3, our key would be 3. All right? So now that we kind of understand the Caesar cipher, let's actually show how it works, right? So there are a few algorithms that it relies on. All right? So the first algorithm we need to know is the encryption algorithm. And the encryption algorithm is C is equal to X plus N modulus 26. Now I'm going to dive into what each of these are. Just give me a second to write them down. All right. Now we have our decryption. And our decryption is the same thing as our encryption process, but instead of an X plus N, it's an X minus N. All right. In modulus 26. Now, you may be wondering what each of these letters stand for, or what each of these variables stand for. So, C represents our character. All right. So, when we're talking about encrypting the word hello, and it's now IFMMP, our plaintext character would be H, and then E, and then L, L, O, hello. So that would be our character, or the letter C. The X represents the index, or basically the placement of the letters. Remember how A has an index of 1, B has an index of 2, C has an index of 3. That's what the index represents. Now N represents the number of indexes we shift down. So remember that shift we were talking about? How each character shifts down a certain number? This whole thing is our key. N is our key. Okay? Now, if you're wondering what the percent sign here is, this is called the modulus. And basically, you know how in division, how you can find the remainder instead of finding the exact result? That's what it does. The modulus finds the remainder. Okay? And this is what I'm talking about, where in the first module I was talking about basic math and things like that. This is where that kind of concept comes in. All right. So let's kind of talk about how we can encrypt using the Caesar cipher, right? So if you did your homework, you should have a Python Caesar cipher file in here. So we can change our directories into the Python Caesar cipher file. Whoops. And if we list, we can see we have all these random files. The only thing you need to worry about is the Python Caesar cipher file, right? So we can do Python 3. Actually, let's I'm gonna use Nano because Vim might be a little advanced for you guys. I'm not sure what your experience level is when you're taking this course, but to make it easier for everybody, we're going to use Nano. So we're going to do a Nano, and then we're going to call this file.txt. Cool. So in here, I'm just going to type in hello world. Cool. So we can do Control O, I believe, and then Control X. Yeah, there you go. So Control Enter, Control O, Enter, and then Control X. So now if we run the file Python 3, the Caesar cipher.py file, it's going to ask us to enter a file name. So we can enter our file.txt file, and then we have options. We can encrypt it, we can decrypt it, we can brute force and exit. Now we don't need to exit the program because we're running this on purpose, right? So let's encrypt the file. So we use 1, and then it's going to ask us for our key to use the shift. So we'll use a shift of 5. Oh, is my numlock not on? 5. There you go. So there you go. It translates it and then it outputs it to this encrypted Caesar.txt. So if we cat out the encrypted Caesar.txt, we can see we have our encrypted message. Hello world, right? Now you can't read it because it says MJQQT BQI, right? That doesn't look like hello world, but that's what it is, but it's encrypted, right? So how do we decrypt this? Well, we can just use the program to decrypt our file. So we can run this again, and this time we'll use our encrypted Caesar.txt, and I guess we can run that, and we're going to decrypt it this time. Now we need to use the same key in order to decrypt it, because we need to go back that shift that we covered earlier. Because if we decrypt it using this shift of 6, it's just going to give us more random text, because that's not the key. We need to use the key, which is shift of 5. So the decryption key right here and the encryption key that we use right here have to be the same. So shift of 5, and it'll translate it and it'll output it to this decrypted file. So if we output that, it says hello world because it decrypted it successfully. All right. So now you may be wondering, all right, so this is cool and all, so now we can actually decrypt and whatever. So if in fact, if we decrypt our encrypted Caesar file that says MJQQT, right, .txt, if we encrypt that, if we decrypt that file with the shift of 6, for example, if we output the decrypted Caesar.txt file, it's not gonna, get the correct, plain text, because that's not the right key. Because the encryption key that we use to encrypt it has to be the same, because it's a symmetric encryption. The encryption key is the same and the decryption key is the same. All right. So now this is cool and all, but a flaw within not necessarily all symmetric encryption systems, but it's mainly specific to Caesar Cipher and a few others, is that it's very easy to brute force. Now, remember I covered brute forcing in the last module, and the reason why decrypting something like this is so easy, or brute forcing like something like this is so easy, is because there's only 26 keys. Because A has an index of 1 and Z has an index of 26. Because Z is the last letter, there's no index higher than 26. So since Z receives a shifted index of 1, it can't recycle back to 26 because there's no other indexes. So there's only 26 keys, okay? So meaning if we use a shift key of like 36, it's just going to cycle over, and the shift key of 36 is going to be the same as 10 because it can cycle back and loop, okay? Now, we can exploit this by decrypting the Caesar cipher, or decrypting this 26 times, right? And each time we decrypt it, we use a key of 1, then we use a key of 2, then a key of 3, all the way to the number 26, right? And one of those will be the cipher. Now we don't want to do that manually because that would take forever, right? So we can actually brute force this. So let's run our program, and we're going to use our encrypted Caesar file that has our encrypted hello world message in it. Now, if we try to brute force this by using option 3, it's going to ask us for a brute force option. We can brute force all the keys using, ranges from 1 to 26, or we can choose a range. Now, the only reason you would need to choose the range is in case if the encrypted text was really long and if you know where the range has to be around. Otherwise, we're just going to choose all keys. Now it says success output written to brute force all keys.txt. So we can output the brute force all keys.txt file. So you can see it tried different keys. So it tried the shift key of 1. try the shift key of 0, then it tried the shift key of 1, tried the shift key of 2, 3, 4, and then when it tried the one with 5, which is the shift key we used, it got hello world. Then it goes all the way up to 26, and 26, so the shift key of 26, which is MJQQT, is the same thing as the shift key of 0, because there's no higher index. There's only 26 letters, 26 possible keys, okay? So you can see we got we were able to brute force this and get the hello world message. Cool. So that's how the Caesar cipher works. Now you can see how this kind of can be dangerous in how easy it is to brute force, right? If you know the key, or you don't even need to know the key. We can just try all 26 keys and eventually one of those will be right. Now, if the file is very long, this could take a long time. This can be very tedious, but the point is still there. And here's another cipher called ROT13, where it encrypts, text and decrypts text, but only using a shift key of 13. So if you literally all of the text is using the shift key of 13. So it's even more insecure because there's only one key, which is 13. Now, I don't know why you would need to use that, but it's there, right? So now we're diving into the topic of the advanced encryption standard, also known as Rigendale, but you don't need to know that, okay? So let's talk about AES, right? So AES is the Advanced Encryption Standard. Cool. AES is a symmetric block cipher that encrypts or decrypts blocks of 128 bits using keys sized at 128, 192, or 256. Okay? The AES, or Advanced Encryption Standard, is a symmetric block cipher that encrypts or decrypts blocks of 128 bits using keys sized at 128, 192, or 100 or 256. Okay? Now remember how earlier in the password hashing module we used SHA-256 or SHA-256? That's because the key that it was used to create that ciphertext is 256 bits, okay? All right, so this encryption method is the currently only publicly available encryption method that is used by the US government, which is pretty cool. Now it is even allowed for the use of encrypting classified data. So this is a very powerful encryption standard, all right? One of the most memory efficient ciphers as well is, AES. It's both memory efficient on a hardware level and a software level. And the encryption rounds of the block cipher will vary depending on its key size, okay? I'll mention that here. So rounds vary. Now, if you remember the block cipher definition, then you should know what rounds are, right? I'm trying to encourage you guys to go back to your notes and learn this, because you guys need to understand this in order to dive into this. Now, AES is a very complicated topic, so I'm trying to make it as clear as I can. But if you guys aren't learning the vocab that I told you guys to learn in the first module, then you guys won't understand this, all right? So go back, review your vocab, and come back here if you're getting lost, all right? So rounds vary on the keys bit size, okay? I'll say number of rounds, just to make it a little bit more clear. So the number of rounds vary, whoops. So the number of rounds vary on the keys bit size, all right? All right, so just to re-clarify, because I know that the AES is very complicated, and I'm not gonna go too deep into this topic. But again, AES is a symmetric block cipher that encrypts or decrypts blocks of 128 bits using keys sized at 128, 192, or 256 bits, okay? So the keys can be any of these sizes, right? So there's AES 128, there's AES 192, and there's AES 256. With that being said, the number of rounds in the block cipher will vary on the keys, or what size of the keys that we're using, right? So if it's 128-bit keys, then we're going to do 10 rounds. If it's a 192-bit key, then we're going to do 12 rounds. If it's a 256-bit key, there's going to be 14 rounds, okay? It's very simple. Now, that's all I'm going to dive into. I'm going to stop right there because already, I'm sure a lot of you are already confused. If you are confused, revisit Module 1. Look through the vocab on block ciphers, look through keys, look through how binary numbers work in bits and bytes, and then remember how the Caesar cipher works, how we had to use a key to encrypt and decrypt that key that we used. Just think of it on the level of bits rather than bytes, okay? Now, let's go ahead and visit a website, right? Now, this website, linked in the course overview, allows you to encrypt AES. Now, we're using AES 256 for a 256-bit key, all right? Now, if we encrypt tree and we just encrypt it, we get this, all right? And this is our encryption right here. Now, remember these double equal signs right here? That's called the padding. Now, I'm going to explain what paddings are, all right? So, because the encryption works in blocks of 128 bits, the cipher will often end with that double equal sign or the padding, right? Now, you're maybe wondering why. So, let's say our plain text is 150 bits. Let me go back here. So, if our plain text is 150 bits, we need to encrypt our first block of 128 bits. Remember, it encrypts blocks of 128 bits. And then it'll do another block of 128 bits, and then another block, right? But if we encrypt, so if our cipher, it works in 128, if we do one round on this like plain text right here, we're only going to have 22 bits left because we encrypted the first, out of the 150 bits, we already encrypted the first 128 in the first process of the block cipher. So now that we have 22 bits left, we need another 106 bits of data to meet the quota of 128, because 128 minus 22 is 106. So in order to encrypt another 128 bits, we only have 22. So we need to add another 106 bits in order to encrypt another 128 bits, right? Because we only have 22. So we need to add at least, we need to add 106 bits. This 106 bits, if we add random data, it's going to create confusion on the plain text because the plain text won't be what it used to be. So what we can do is use the padding, right? So we'll just throw in a bunch of equal signs until it reaches that quota of 128, and then we can encrypt it, and then that basic random data of 106 bits that we filled in there can just be represented with the double equal sign, all right? So that's what those double equal signs are for, right? We're basically filling up the amount of bits we're missing in order to do another 128 bits of encryption, all right? So that's what the padding's there. If you need more description or if you're still confused, just go on the course overview, okay? Now, if you want to learn more about AES, because it is a very complex topic, I'll have some links on the course overview you can check out, all right? Now, last is just the homework, all right? Your homework is very simple, very easy to do. All you have to do is read this article that is linked in the overview for this course. And this is the last homework assignment, I think. So again, it's just reading. Just read through it. Even if you don't fully understand it, just read it and try to understand it, okay? But that's going to be it for this video. So make sure to, you know, leave a like and all of that. And I will see you guys in the next module, which is asymmetric encryption. And this one's actually pretty cool as well. It's similar to symmetric encryption, but not exactly, right? We're going to dive into that later. So regardless, make sure to leave a like on this video, subscribe, do the whole YouTube algorithm thing, and I will see you guys in the next one. So stay happy, stay positive, and as always, happy hacking.